So my name is Raul Marrero Rosa. I'm right now a postdoc at Northwestern University working with Professor David Core and Gianluca Cusatis. My PIs of my PhD defense were David Core and Professor Surendra Shah. And I will be talking about contact mechanics insight on carbon nano-reinforced composite interaction, so an interface between the carbon nanotubes and the cementitious composites. That is part of my PhD thesis. So on our group, we are working on carbon nano-reinforced cementitious composites. So we either have multi-wall carbon nanotubes or carbon nanofibers in a very low concentration, from 0.08 to 0.15 weight% of cement. And we added an aqueous solution through the cementitious matrix. Here you can see like the carbon nanotube fibers that are well dispersed around the cementitious matrix. This is an optical image from Confocal microscope. How we do the dispersion? So we use a superplasticizer as a dispersant that we add to the water, and we have powder form of multi-wall carbon nanotubes and carbon nanofibers. Then add ultrasonic energy to mix the to do the dispersion of the system. Then we have like a black water or dispersive suspension, and then we can use ultraviolet visual spectroscopy to see how well dispersed the systems are in the aqueous solution. What we achieve with adding these carbon nanotubes, with also works from Professor Maria Consta, we have that there was a decoupling between the compressive strength and the elastic modulus with only 0.1% of CNF CNT. And this is a way of increasing the elastic modulus with a cost-effective or more resilient type than increasing the compressive strength or with adding more cement to the system. From data from a previous student in our group, Yuan Gao, she was working on the interface between aggregate and the cementitious wall phase, and she found that there was an increase of calcium silica hydrates on that region and an increase in the elastic modulus with atomic force microscopy of the samples that have the 0.1 weight% of CNT. Another property of this material from Professor Constant's work is that you can use well-dispersed carbon nanotubes to be a sensor, so self-sensing the load that is being applied. But one question that is not answered is what factors are affecting the interaction strength between the carbon nanotubes and the cementitious components in the system. And this is to illuminate how is the interaction between the matrix and the carbon nanofiber or the fiber with the matrix. So I did fundamental contact mechanics measurements. So first is this is one part of my thesis. So the first two parts. First is doing grinding and polishing procedure for contact mechanics to have a very low roughness surface. And then I developed AFM tip that is CNT coated tip that I can measure the adhesion strength between the surface of the sample and the CNT in the tip. So standard procedure of polishing, we have very small samples of cement paste, 2 by 2 by 8 centimeters. Then we cut it with a diamond saw and embed it in epoxy. And then we have a polishing procedure to get a low roughness on the surface of the cementitious base. We can use either atomic force microscopy tapping mode or the Olympus 3D laser to acquire the topography of this surface. And this is usual result from the AFM and a usual result from the confocal microscope. So they have similar resolution in terms of what roughness you can calculate with both systems. So here 490 and 400 in system where you have the aggregate on the system, like there is sand on the system. But this confocal microscope is faster, and also you can get a larger area to calculate. For only cementitious material, we got average roughness of 40 to 70 nanometers in the roughness after applying the polishing procedure. So that's more in the sample preparation for doing the adhesion test. In the part of adhesion test, we have this developed multi-wall carbon nanotube tip that will acquire adhesion of forces. So this is a schematic. So here we have a silicon oxide particle that is coated with oxidized multi-wall carbon nanotube and is glued to a tipless AFM with epoxy. And then we perform like a peak force test where we apply a force displacement of the tip until we touch the substrate, and then we pull it away, like pulling a tape out of the surface. And we can measure here the adhesion force between the CNT and the substrate. How you prepare the CNT particles? So we follow a layer by layer procedure in which we have silicon microparticles. Then we attach to it polymer PDDA that is a surface coating of the system. Then polyester sulfonate, a third coat layer, and then another PDA layer. So here you can see after 3 coatings, we have the PDDA, and what we want in this coating is the ammonium part of the polymer, because then we can attach the oxidized CNT to the ammonium polymer. And this is the particle that we will use for the AFM measurement. So we attach the AFM with epoxy, and first we measure if we didn't cover the particle with epoxy when gluing it. So here we have carbon 90% concentration, and this particle wasn't covered in the procedure of gluing it. So then we go to our sample. That the control sample is silicon wafer, and we can get adhesion test, adhesion force versus indentation force. And when you have more indentation depth, you have more adhesion force, since you are increasing the area of contact of the system. And this can be seen in this image where we plot the adhesion force and indentation depth, and then I normalize the adhesion force by the area of contact that is a function of the indentation depth. And this gives you that there is adhesion strength of 8.37 between the CNT and the silicon wafer. And we compare it to our initial concept that we were thinking on gecko adhesion. So they have like addition of gecko is around 10 microcentimeters square. Vertical aligned multi-wall carbonate nanotube 11.7, and our work 8.3. So they're in the same magnitude of measurements. But we didn't want to only do the adhesion force on homogeneous substrate, like silicon wafer. So when we go to cementitious substrate, we have different phases in the heterogeneous system, and we will be using a Gaussian deconvolution process from Professor Raul, and to get the different phases, Gaussian phases that contribute to the overall measurements that we are doing of adhesion strength. But I need to take both measurements in the same area, and that's the reason I use my second bachelor's degree on surveying, and I made some benchmarking on the system to know the reference for the system of the measurements that we will do in the atomic force microscopy and the SEM-EDS. So I measure the surface roughness near the benchmarking, and then I go to the AFM to a region near that benchmark and get the distribution of adhesion strength for different sizes of the atomic force. Here we have 1 micro, 1 micro. This one is 10 by 10, 5 by 5, 10 by 10, and 25 by 25. And these are the distribution of the system, and mainly we seek two peaks. One with lower adhesion strength than the other. And in the systems, if we do acquisition size that is very small, we will concentrate localize the measurement to one of the phases. And if we do a larger coarse grid, we'll have more data from the material that has more surface in the system. So position between the 10 micro and 25 micro and 15 micro, 5 micro and 10 micro give you the two phases that we're taking measurements. One interesting thing is that in the surface that we have this globe formation, this particular to CSH, we have a lower adhesion strength than the part that we have intermixed region in the system. So we were thinking that this CSH is interacting less with the carboxyl groups of the CNF, but we didn't know why yet. So we start to the chemical characterization. So here we have the atomic force microscopy image, and it's a 25 by 25 region, and this is the atomic force, the confocal microscope region, and here we have in the confocal microscope region the one where we measure the adhesion force. So we can know now we know where to do the SEM-EDS to get the chemical characterization. And this plot is the adhesion strength versus calcium to silica ratio. And we saw that for calcium to silica ratio lower than 2.5, that is for CSH, we saw a decrease in the adhesion strength with the multi-wall carbon nanotubes are functionalized. And this has been shown with molecular dynamics of GO and different calcium to silica ratio CSH that is due to the interaction of the amount of calcium that is in the system and the oxygen groups in the CSH. So main conclusion of this research was that we developed this multi-wall carbon nanotube coated AFM that you can use different substrate, so you have to only change the substrate to get adhesion between different substrate. Then the benchmarking technique allows the correlation between the mechanical AFM measurements and the chemical SEM-EDS. And the calcium concentration of the CSH will be controlling the interaction of the multi-wall carbon nanotube, or the interface between the multi-wall carbon nanotubes and the different cementitious systems. I want to acknowledge my sponsors, NSF, and ExxonMobil, my COSATIC group, collaborators, and all the labs that I use on Northwestern for different parts of the procedure within my thesis. Thank you. And